Well, hello, welcome again. We're having a look into our journey into number theory, and we're looking at tutorial problems for Chapter 3, Section 4, and these are questions 15 and 16. So 15a, we start off by defining this phi sub 2 of n to be the sum of the squares of the numbers less or equal to n and relatively prime to n. And I give you this sum here, which is not easy to prove, but you might like to see if you can give a proof of that yourself, but here it's just been given. It's the sum over the divisors of phi 2 of d on d squared. Turns out to be the sum of the squares from 1 up to n divided by n squared. And we want to show that this phi sub 2 of n can be written using phi and phi inverse. So that's what we're going to have a look at here. I'm just going to do, in fact, the second bit here. This will follow, in fact, from what we did above, but we'll just do this little bit here. So here is the worked solution for this. So we're given here's our phi of 2, and we're given this sum. And I'm just going to add up this sum. This is a well-known series. It's 1/6 nn plus 1, 2n plus 1, and I can divide by the n squared. Cancel out one of those, so I get 1 on 6 nn plus 1, 2n plus 1. So that's given by that. So I can now use Merbius Inversion, again such a useful tool, and I can get my hands on this thing by using Merbius Inversion. And that'll be the sum of this multiplied by mu n over d. Now I just expand all this out in here, so I get 3 terms once you expand it out. And again I can then split up this into 3 sums. So I get 1/3 d divides n mu n over d times d, that's from this one. And I'm going to get 1/2 just mu n over d, plus 1/6 mu n over d all over d. Now, of course, this sum in the middle is really just the sum of mu d, sum over the divisors of n, and we know that sum is 0. This one here we've seen before. This one is just phi of n, and this one here is when I take the n squared in, take the brackets there, so I'm going to get n squared on 6, sum over the divisors of n. I can just take the divisors in the opposite order and rewrite this as mu d over n, and I can take this n out here and cancel, and then this one here in fact gives us that product that we had in the question, but we've seen before this is just equal to phi inverse of n. Gives us a nice expression for this phi 2 of n, the sums of the squares of the numbers that are less than and relatively prime to n in terms of phi and phi inverse. These inverse arithmetic functions are very interesting objects. Well, similarly one can define phi 3 of n to be the sum of the cubes, and I've not gone through the calculations, but that's what the final answer is. You can write this also in terms of phi of n and phi inverse of n. So it's n cubed on 4 plus n squared on 4, phi inverse of n. Question 16 is simply a nice little result using the Dirichlet derivative, just a bit of practice with that. So firstly we want to show that the convolution of u and u is Tor, and if we start, we can apply then the Dirichlet product rule to this, the Dirichlet derivative, and we can arrive at this little formula here, that Tor of n log of n, that is the derivative of the Dirichlet derivative of Tor of n, is just twice the sum over the divisors of n of log d. Very simple exercise, this one. In fact, if you take the convolution, u of n, remember, is just equal to 1, so this just gives me the sum over the divisors of 1. The divisors of n, you write down 1, well by definition that's just Tor of n. Now the interesting thing is if we take the Dirichlet derivative here using the product rule, so we get first by the Dirichlet derivative of the second plus the second by derivative of the first, which is just twice u dashed. And the Dirichlet derivative of tor of n is just tor of n log n by definition. So I can write that then as writing out this convolution, then u is just 1 and the derivative of u is 1 times log. And we're taking a sum over the divisors of this because it's a Dirichlet product, and that gives you the result. And they were just the two questions for that section.